Okay, so we're going to continue on our design example. In our last exciting episode, we found out that D is 18.65. But we're not going to use D is equal to 18.65. We're going to say that D is equal to 18 inches. It's a nice round number, and it's going to match better with form manufacturers. Now, this is design and not analysis. You could make it 20, and you wouldn't be wrong. Because we're going to see as we go along that there's a lot of other problems that are going to come in here that make all these numbers that we're calculating so far, they don't have to be very precise. If our cover is 2 inches, that means that our H value is equal to 20 inches. That calculation is not called design. That's detailing. Okay? So detailing is the provision of all the other pieces of information that you need to construct the beam that don't go into the analysis. Because in the end, we're going to have a beam that we're going to give to somebody and say, build it. And their responsibility is going to be build it in accordance with the plans and specs, not redo the analysis. So we have D set at 20. That's pretty cool. So let's go see where we're going. So we know now that B is equal to 16 inches, that our moment we're resisting is 313, and we've calculated that D is equal to D is equal to 18 inches, and we had a value for rho, right? Rho was 0.0143. Yes, 0.143. So that's pretty cool. Now we have to detail the steel. And this is where it gets to be interesting. A sub S is equal to rho BD, right? Definition of rho, which is equal to 0.0143 multiplied by 16 multiplied by 18. What does this come out to be? I'm going to show the kids at home how my calculator works. You're not kids. But I do have something on my in my office at home that says if you don't go up by 50, you don't have to. So I'm the kid. 4.12 square inches. Great. So we get on the phone, we call the steel mill and we say, yes, could you send us over one bar that has a cross-sectional area of 4.12 square inches? What's the plant going to tell me? Oh, there's nothing you can't acquire with the proper application of money. So if you call the steel mill and you say, I don't care what it costs, get me that bar, they'll make it for you. But it might cost a lot of money, right? You're probably now going to fail step number 1 in being a successful contractor, which is win bids. So what are we going to do? We need to find out a number of bars that give us A sub S is equal to 4.12 square inches or thereabouts. Right? We don't need it to be exactly 4.12. That's why they call it design. We're going to make a selection. We're going to go to our friendly neighborhood design aid. We're going to say, okay, here's my design aid. Here, this gives me the bar number size. Number 4, number 5, number 6, number 10, number 11, number 14, number 18. And this gives me the number of bars, 1 through 12. So I can look around here. Well, I got, let's see, this would be slim pickings usually. This never happens. We're doing a different example from the one we did in the class. This never, ever happens. Is that 4.21 in there? Okay, am I reading it wrong? That's what we want, right? 4.12, okay, good. I was going to say it never happens. Good. Still had never happens. 4.2, well, that's pretty close. I'll take that one. I don't like that, I don't like that, don't like that. I could use this, but I'd have to check. I don't like, unless I made D slightly smaller, I don't want to make area steel too small. And I'm not seeing, anybody see any other good ones up there? 4.42, that's worse. That looks like a good one, right? 7 number 7s. Go 7 number 7s. 7 number 7 bars. A sub s is equal to 4.21 square inches. Right? It's not what we wanted. And that's why we didn't stress over whether B was 18 or 20. Because it's still not what we wanted, right? Now we have to check something else in the detailing. Will 7 number 7 bars fit inside a 16-inch wide beam with an inch of cover on either side? Do the bars fit? Well, if I have a beam, and if I have n sub b as the number of bars, the diameter of the bar, we can look that up, and this is the spacing. S sub b is the spacing. The spacing is easy to remember. It's equal to 1 inch or d sub b, whichever is larger. That comes from the code. Remember we talked about bundled bars a while ago? You can also bundle these if they don't fit, but let's check. This distance from here to here is the cover. So if I go from this distance to this distance is 16 inches. I have to check 16 inches is what I have available. And what do I have? If I walk across here, I have the beam width required, or minimum, is equal to n sub b multiplied by the diameter of the bar plus n sub b minus 1, because if you have 10 bars, you have 9 spaces, multiplied by the spacing of the bars, plus 2 covers. Well, that's easy. And number of bars is 7. This is 7/8 of an inch, plus 6 times 1 inch, plus 2 times 1 inch. Cover on the side of the beam, we look it up in the code, it's supposed to be an inch. And now we can check that. We got die 49 over 8 plus 6 plus 2 is 14.13 inches, which is less than 16. That's okay. When you go to put those bars into the beam, they're going to fit. So that's good. That's part of our detailing. Can the because if you can put in 25 number 7s, they won't fit, right? And then the beam will have the capacity on paper that you need, but it won't be constructible. And that's when someone says, hey, this doesn't work, what do you want me to do? And then you say, oh, I want you to do this. The bar says, yeah, that costs a lot more than we originally bid. We'll be letting you know how much. So we have AS is equal to 4.21 square inches. B is equal to 16. D is equal to 18 inches. Is our beam adequate? we've got this far only to start a new problem. This is where we used to start. We've got a design. Is it adequate? It's probably okay, but I need to check because I moved D around and I moved A sub S around. So let's check. We know that rho is less than rho max. I'm going to check, right? So rho is equal to 4.21 over 16 times 18. And that's equal to 0.0146. Okay, rho is less than rho max. We know that phi is equal to 0.9. When all of this is true, we also know that A is equal to ASFY divided by 0.85 F prime CB, which is equal to 4.21 multiplied by 60 divided by 0.85 F prime CB. A is equal to 4.64 inches. Our nominal moment capacity is AS F sub y D minus A over 2, which is 4.21 square inches multiplied by 60 kips per square inch, multiplied by 18 minus 4.64 over 2. (3,960 kip inches). Over 12 is equal to 330.06. What was our required? That's M sub n, phi, M sub n, anybody got it, since I can't seem to operate my calculator to do today? Is 297.0, is that correct? Yep. So that's fail, right? Increase D. D is equal to 20 inches. And repeat. So rho is equal to AS over BD, so AS is equal to 0.0143 BD, which is 0.0143 BD, which is 16 multiplied by 20 now. And that area of steel is equal to 4.58 inches. Back to our design guide, 4.58. It's a possibility. Like that. Really don't like that. We'll go with 4.71, 6 number 8s. It's 4.71 square inches. So now we have our steel design. We check 2 covers plus 6 1-inch bars plus 5 1-inch spaces is going to be, not requiring a calculator, is 13 inches, which is less than 16. The bars will fit. Right, so this is the cover, 2 inches, plus 6 bars at 1 inch, plus 5 spaces, also at 1 inch. Number 8 bars happen to have a diameter of 1 inch, right? So if we know that, then we go back and we do our check. Rho, we already know, is 0.0143 because that's how we figured out what A sub S is. So this is rho less than rho max. Phi is 0.9. And we get A is equal to ASFY over 0.85 F prime CB, which is what we've been doing all along, and now AS is equal to 4.58. A is equal to 5.05 inches. And our nominal moment capacity is equal to ASF sub y, 1 minus D minus A over 2, which is equal to 4.58 multiplied by 60, divided by 20 minus 5.05 over 2. Is equal to 4,802 kip inches multiplied by 1 over 12 to convert to feet. And that's 400 kip feet. And I multiply that by 0.9. I'll get 360 kip feet, which is greater than 313. Okay, then I can draw my beam. Right? D is 20, so this is now 22 inches. This is 16 inches. 6 number 8s cover 2 inches, and F prime C is 4 kips per square inch. F sub Y is 60 kips per square inch. Well, that was no fun. Because now I'm looking at it and say, well, 360, I'm more than 10% over. I'm going to go back. Maybe maybe what I should do is take the beam deeper, or go back to 18 and beef up the steel a little bit. And that'll probably give me the right answer. Won't that be fun, redoing it over and over and over again by hand? Sam, you're shaking your head no, but what you meant is yes. Yes, it would be fun. This mathematics is the greatest thing ever. It's so much fun, I wish I was doing more of it. I don't want to do anything more either. I was disappointed because I thought my 18 was going to do it. So I didn't want to do another one. And if I don't want to do another one, you can imagine where you end up. But it shows you how we can design these beams and we can design them in many, many ways. So how do we determine which of our beams, which we could get many, many different ways, which of our beams is going to work? One of them is we can look at efficiency of beams. Efficient beams have a ratio of D to B of about 3. So 20 to 16 is not very close to 3. The beam is inefficiently using the steel. Because I could make D 45 inches, then I'd hardly need any steel in it. But it might have another problem then. It might bounce too much. If you've ever been on a bridge, traffic got stuck on one side, and traffic's moving at the posted speed on the other, anyone ever had that experience? The bridge will move. Because most people will experience that bridge at high speed. And there'll be so much bumping around going on with the suspension in their vehicle, they won't notice the bridge is moving. So it doesn't pay, it's not worth it to make the bridge too stiff. But if you walk down the hallway of a building and it starts to bounce up and down a little bit, what are you going to think? Where's the nearest exit? So the amount of deflection that we get under a given load is also a design criteria. We have to check, make sure that we don't, even when the beam is fully loaded or the structure is fully loaded, that we don't get too much deflection, because people don't like deflection. The CN Tower is the tallest freestanding structure in the world. I think I may have talked to you about it earlier on. And it is now just in the Western Hemisphere. The structural engineer in a design meeting said, wouldn't it be neat to have a little inclinometer? It's a big long tower with a big bulb on the top, and tell you how far over the bulb has moved from the center line in the wind as it's moving around, which is really cool from a structural point of view. And the architect said, are you kidding me? People don't think buildings move. But the compromise was if you ever go there's an observation deck, and there are windows that look straight down, and you can look straight down and you'll see that the structure is moving, and it's moving quite a bit, because otherwise it's expensive. So deflection is going to give us problems. So is shear. Now, on Tuesday, I had an older version of my software that I didn't think I had. It's just an Excel spreadsheet software. And it was kind of messed up. So I recorded, and I'll put up on the Canvas site how to use it. And what I wanted to do is spend about 15 minutes and talk about where we get these moments from, number one, and number two, how we can reduce the cost of our beams by removing bars where we don't need them. So is everybody, who here has had a good experience with drawing shear and moment diagrams? You like them? Good. I didn't say experience, I said good experience. Aren't they fun to draw?
Probably worse.
I'm sorry?
There's probably worse things.
Yeah, you can have a root canal from time to time. You'll find out that that's worse, right? But they can be complicated. And so I'm going to talk to you about how we're going to do structural analysis. Let's take a look at a simply supported beam, which is what we've been looking at all along, right? This beam is simply supported, and let's start with an easy one. This beam has a uniform load on it, W, which is equal to 120, say 1,200 pounds per square foot, which is 1.2 kips per square foot. Can you draw the shear and moment diagrams? How long is it going to take you? How long is it going to take? I said I was going to do it in 15 minutes, right? Yeah. So it's got to take at least less than 15 minutes. So I'm going to show you how long it takes. It takes no time at all. This is a common problem. And so engineers face this common problem all of the time. And why reinvent the wheel? The same reason we don't recalculate R sub n max every damn time. If this is our loading condition, right? We have W is our uniform load, that the total equivalent uniform load is WL. The reactions are equal to the shear, which is WL over 2. The maximum moment occurs at the center, it's WL squared over 8. And that's all we'll use. This is from the steel table, believe it or not. But it works very nicely, and that's all we're going to do. You do this in steel. You look these things up, right? So we can now very quickly compute what happens. Does Dean tell you about superposition? Right, that if I then have a single point load, that I can add the two of them together?
Yeah, I remember hearing about that.
Right? So superposition means if I can break it down into 3 different loads, then I can add them all together. So if I now decide I want to have a single point load 2/3 of the way over in that beam, then I've got to go to my guide and go to my guide and find what I want. May have to look in a different textbook. Oh no, there we go. So then I could go to this. All right? This problem is what happens to you if you have some low point load somewhere on the beam. I don't care where. Well, tells me what the shear is. Tells me what the moment is. And this is, this one's cantilever. I have to find a simply supported beam. What am I doing, Kevin? Simple beam. Simple beam, there we go. Okay, simple beam, right? Concentrated load at the center, concentrated load at any point. And if I take those two, if I take the distributed load plus that concentrated load, I just add the moments together. And you can see that this also, does Dean cover that equation, that it says the moment at any point x is given by this equation? Right? Does he cover that? Anyone want to commit to it? Isn't someone taking 450? Does he cover that?
I mean, I've seen these tables.
Been a few weeks since we had class.
Yeah.
Been a few weeks since we had class.
Okay.
We're a little rusty.
But I've seen you try to see.
Rusty and steel, get it? There's the first. Very good. So we'll be looking at these a little bit when we do structural analysis. But simply put, I'm going to take that moment, that equation, right? It says when moment at, go down, m is equal to, well, that's at the center. No, sorry. M is equal to any value of x. Where's the equation, Kevin? Yeah, you get the equation for that straight line, the equation for this straight line, you add them all together, and that'll give you the moments. And so the moment is going to be, pointing at the screen doesn't help the people at home. This is going to give me shear, looks like this. And this is going to give me a moment that looks like this, right? And here I'm going to have m sub max is going to be equal to PL squared, or WL squared over 8. WL squared over 8, where L is the clear span. And so I design a beam at 313, and I find out I need 6 number 6s where the maximum moment occurred. How many number 6s do I need at the end? What's the moment at the end? 0. How many number 6 bars do I need? No, I need row min, right? So I know row min, and if I go, what do they have, 16 and 20 gives me 32 square inches. Divide that by 1 over 3, I need like 0.01. I need a number 4 bar. Probably put 2 there so that the contractor doesn't screw it up too badly. But that's the detailing. So somewhere in between, I need fewer bars. And if I terminate those bars as I go along, I make the beam cheaper. And so we're going to talk about how to calculate where those termination points are, the efficient termination points are, and then what we do to make sure that we get development. If you remember the first day as we were together, we talked about if you try to grab just the end of the pencil, it doesn't work. You need some development length. So that's where we're going. Did it in 10 minutes. Any questions? So I think everybody did